Are you ready, Professor Richard?
Yes.
Okay. Okay. Good afternoon, everyone. Thank you for coming and join to the online 3-in-1 professor visiting professor. Today we will continue our meeting, our lecture yesterday, last week. Today we will hear from the Professor Richard about the transformer. So, similar with last week, first Professor Richard will give the materials, and then we will discuss and Q&A. So, without further ado, Professor Richard, please, time is yours.
So is my voice clear?
Yes, I can
Okay.
hear your voice clearly.
Yeah, because I think I should log into the meeting room before I wearing my earphone. But now it seems that my earphone doesn't work.
Yeah,
Yeah,
I think
so
it's still clear, Professor Richard.
okay. Yeah, so I cannot use my earphone now. Yeah, let's just start.
Okay. For all of the participants, please show your camera.
Can you all see my screen?
Yes, Professor.
Okay. Okay, good afternoon. Today I'm going to introduce transformers, which is the most successful model for natural language processing since its release. So this paper describes the details of the transformer models is entitled Attention is All You Need. It is not very easy to read because the authors assumed that the readers have background knowledge. So I hope the class help you to understand this paper, and then you can read it. So transformers is designed for sequence-to-sequence tasks. Its application include machine translation, chatbot, and summarization. In machine translation, its input is the source language sentence, and the output is the target language sentence. In a chit-chat chatbot, the input is the user's utterance, and the output is the chatbot's response. In summarization, the input is the source document, and the output is the summary. Okay, sorry. So here we can see that on the left-hand side, you will find a flowchart of transformers from here to here. We will break down the model step by step. The dashed line, rectangle highlights the current step. To start, transformer takes the input sentence and looks up the word embeddings and looks up the word embedding vector for each token. In this example, it retrieves 4 vectors for "Hi, how are you?" So imagine that the vector representing "Hi" is 0.1, 0.54, 0.29. Now I will describe positional encoding and its purpose. Since transformers don't process tokens one after the other from left to right, we must incorporate positional information. That's precisely what positional encoding is designed for. The creator employed a clever technique to calculate the values for positional encoding. When it comes to positional encoding, odd numbers like 1, 3, odd number dimensions are computed using the cosine function. And while even numbered dimensions utilize the sine function. When you add the input embedding to the positional encoding, it becomes what we call positional input embeddings. In simpler terms, this process ensures that the value of each dimension at each position is distinct. Now, let's delve into the encoder layer. This layer consists of 2 main parts: the multi-head attention submodule, abbreviated as MHA, and the fully connected submodule, abbreviated as FC. So the encoder layer takes the positional input embedding as input and generates the encoder input representation as its output. So now we are dive into the mechanism of multi-headed attention. To begin, we will explain the center concept in this session, self-attention. Self-attention measures how much attention each token in a sentence pays to every other token. So we can see that in this sentence, we can calculate how much attention U pays to R, U pays to how, U pays to hi, and U pays to itself. We break down the positional input embedding of a word into 3 parts: query, key, and the value. Using a series of linear transformations. In this case, each of the 4 words is transformed into its own set of query, key, and value vectors. So we can see that these 4 words correspond to these 4 queries, these 4 keys, and these 4 values respectively. When we multiply the query matrix with the transpose of the key matrix, we obtain the scores matrix. Let's assume that this is the scores matrix. So we can see that we have the correlation or self-attention between how "Hi, how are you?" These 4 words. We also need to take into account the dimensionality factor. So we divide the entire scores matrix by the square root of dk, which represents the number of dimensions in the key. So in this example, dk is 3. To ensure that each row behaves like a probability distribution, where the sum of attentions in each row adds up to 1, we apply the softmax function to each row. As previously explained, the softmax function enhances the largest value while maintaining the smallest value. So we can see that although in the beginning, how are you has very small value and high high has the highest value. This kind of function makes high become larger, but also keeps the values of how, r, and u. And next, we multiply the attention weights by the corresponding values, which gives us the output. Following our explanation of self-attention, let's now discuss multi-headed attention. Recall that we employ a series of linear transformations to create sets of queries, keys, and the values. If we use n sets of these transformations, we can produce n sets of different queries, keys, and values. So if we have 2 sets, then we have 2 heads. If we have 16 sets, then we have 16 heads. This concept is referred to as multi-headed attention. The diagram illustrates this when n equals 2. Now we combine the output from both heads by stacking them together. Now, so we can see that for each word, its dimensions become increases from 3 to 6. Then we apply a linear transformation. This gives us the final computation results of the multi-headed attention component. So you can see that we are now here. We've just explained how multi-headed attention takes a positional input embedding of a sentence as input and produces an output. In practice, we include the original input in the output to retain some of the input information. This is the well-known residual connection, which assists in the flow of gradients. So we can see that we are now here. Next, we apply layer normalization to the combined result. that is the original input and the output. Now let's introduce two types of normalization techniques. Both the first type is called batch normalization. It involves normalizing values within the same dimension. For example, on the left-hand side, we have three vectors. In the first dimension, the mean is 3, and the standard deviation is 3. We then use this mean and the standard deviation to normalize the values within the first dimension. As shown on the right-hand side, for the first vector, on the right-hand side, we have another kind of normalization called layer normalization. It focuses on normalizing values in the same vector. So as shown in the right-hand side, for the first vector, the mean is 2, and the standard deviation is 2. We utilize this mean and the standard deviation values to normalize values within that specific vector. So we can see that let's take a recap. For batch normalization, we normalize based on each dimension. And for layer normalization, we normalize based on each vector. Okay, so next we pass the result through a sequence of steps. One linear transformation, one linear transformation, a Relu nonlinear transformation, and then another linear transformation. Finally, we arrive at the result, and we apply layer normalization again to it. Just like before, we also include a residual connection to facilitate the flow of gradients. So now we are here. We've now covered the MHA and the FC components. Together, these form the transformer encoder, which serves the purpose of generating input representations. So then we can stack the transformer encoder, shorted as TE, n times. For example, the famous BERT-based model has 12 layers, where BERT large has 24. Next, we will discuss the transformer decoder, which is the counterpart of transformer encoder. It generates output tokens in an auto-regressive manner, just as the animation demonstrates. So in this animation, we can see that when we see "Hi, how are you?" in encoder, then we generate start, and then we use the first 5 to generate I, and then use the first 6 to generate M, and use the first 7 to generate phi. and the end. Now, let's delve into the specific. Imagine the decoder has already generated the sequence I am fine. We skip the process of generating I am fine. So we employ the same method as with the input tokens to generate positional embedding, positional encoding for each output token. Next, the positional output embedding must undergo processing by multi-headed attention mechanism. So now we are here. And then the key, we must explain the key distinction between the decoders and the encoders multi-headed attention is that the decoder's MHA doesn't consider tokens that comes after the current token. So in this image, you can observe that for the token start, the token following it have been crossed out. During this process, attention is solely direct to start. So if we take the look at the token I, then we can only put the attention on start and I itself. So in order to achieve this, we introduce so-called look-ahead mask, which is essentially a matrix. The purpose of this matrix, the purpose of this mask is to prevent tokens from attending to any tokens that comes after them in the sequence. To do this, we set the values in the masks corresponding to a token and any of its following tokens to negative infinity. For example, if we have a token at position 1, we set the values in the mask at 1, 2, 1, 3, and 1, 4 to a negative infinity. When we add any value to negative infinity, the result remains negative infinity. Therefore, in the result matrix, these entries in these positions will still be negative infinity. This effectively ensures that the decoder's MHA only attends to tokens that precede the current token in the sequence, just as you described. So we can see that this is the final result. All values following the current token becomes negative infinity. Exactly after the look-ahead mask to the scaled scores, we proceed to apply the softmax function to each row in a manner similar to what we do in the transformer encoder. This softmatrix operation ensures that the tokens that should not have attentions will effectively receive very low attention scores, essentially approaching 0. This way, the decoder's multi-headed attention and the mechanism focuses on relevant tokens preceding to the current position, while minimizing attention to the tokens that follow. So we can see that for AM, it puts most attention on itself and puts some on I and puts some on the star token. Now the image illustrates the placement of the look ahead mask within the multi-headed attention mechanism. The output of the first MHA determines how attention distributed of how the attention is distributed over the decoder input. Now, so now we just explain what we get here, and now let's delve into the details of the decoder's second multi-headed attention. This type of attention is unique because it spans both the encoder and the decoder. We can see that the decoder's information passes through this link to the decoder and is appropriately named encoder-decoder attention. In this particular layer, the encoder's output plays a role in generating the queries and the values, while the outputs from the decoder's first MHA are used to generate the keys. So let me repeat. The encoder's outputs plays a role in generating the queries and the values. If you remember, query, key, and value, the encoder's output generate queries and values, while the output from the decoder's first MHA are used to generate the keys. I will explain it more after this picture. The interaction allows the decoder to attend specific part of the input sequence produced by the encoder, helping it generate meaningful output tokens based on the information from both sources. When we multiply the query vectors from the encoder with the key vectors from the decoder, we compute the attentions across all input tokens and output tokens. These attention scores are then stored in the scores matrix, representing how much each input token should contribute to generate the output tokens in the decoder. So let me repeat. These attention scores are then stored in the scores matrix, representing how much each input token should contribute to generating the output token in the decoder. Certainly, it is important to account for the dimensionality factor. To achieve this, we divide the entire scores matrix by square root of dk, where dk represents the number of dimensions in the keys. In this specific scenario, dk is set to 3. So in a similar manner, in order to transform each row into a valid probability distribution, where the sum of attentions in each row equals to 1, we apply the softmax to each row. As we explained earlier, the softmax function serves to amplify the maxima values when preserving the relative proportions of the minima values within each row. So indeed, by multiplying the attention weights with the corresponding values, we can calculate the output. This operation combines the attention scores with the relevant information from values to produce the final output for the second for the decoder's second MHA layer. So now we proceeded to here almost the end of the output of the decoder. The output vectors undergo a series of steps, including one layer normalization, a feed-forward layer, and another layer normalization. We will skip this part because this has already been introduced in the encoder section. Afterward, each resulting vector is further processed by a linear layer, and then normalized using the softmax function. This step helps generate the probability distribution for the next token over the entire vocabulary, because the dimensionality of this vector is the size of the vocabulary. In a sense, it determines the likelihood of each word in the vocabulary being the next token in a generated sequence. So in the end, the word with the largest probability corresponding to the end symbol. This symbol signifies the conclusion or endpoint of the generated sequence. So finally, the decoder select the end token as its output. Up to this point, we've covered the process of the transformer decoder. It's worth noting that you can also stack the transformer decoders n times, just like you can with the transformer encoder. Stacking multiple decoder layers allow more complex and expressive modeling when generating sequences or performing various sequence-to-sequence tasks. For example, if you have taken a look at the current large language model, they use the transformer decoders as their main architecture. So the famous Llama 7B or Llama 13B, 13 billion parameter model used over 40 transformer decoders. Okay, so following the development of the transformer model, the same research team discovered that the encoder component of the transformer could be used independently and provided to be highly valuable for a range of natural language processing tasks. Indeed, the research team authored a paper titled BERT, Pre-training of Deep Bidirectional Transformers from Language Understanding. This paper introduced the BERT model, which made significant advancements in the field of pre-training models for language understanding tasks by utilizing the transformers bidirectional encoder. BERT's innovation approach to BERT's innovative approach to pre-training played a pivotal role in improving performance on a wide range of NLP tasks. So you can observe that this specifically covers the encoder portion of the transformer model. BERT has the flexibility to accept either one sentence or two sentences as input. Just like in the original transformer model, for each token, we combine its token embedding, segment embedding, and the positional embedding. The resulting list of embeddings is then input into the first bidirectional transformer encoder. Subsequently, the output from the first encoder is passed to the second encoder, and this process continues. The output from the final encoder can be regarded as contextual embeddings for each token. These contextual embeddings can be used as input to the task-specific layer to carry out various downstream NLP tasks. For instance, when the input is "I like strawberries," it's rather surprising that it's split into 6 tokens, not just 3. This is because BERT adds special tokens at the beginning and end of the sequence, namely CLS and SEP. Furthermore, to reduce the vocabulary size, BERT's tokenizer also breaks down some lengthy words into shorter subwords. So for example, strawberries is split into straw and berries and sharp berries, with sharp indicating that berries is not the initial subword. After this tokenization, BERT fetches the embedding vector for each token from token embedding file, and each vector has 768 dimensions. So we can see that each input corresponding to a 768 dimension vector. So COS is 768 dimension. I has 768 dimension, and so on. Now, let's delve into BERT's pre-train process. We use the term pre-training to differentiate it from the training of BERT on downstream tasks. The remarkable aspect of pre-training BERT is that it doesn't rely on human labeled data. So a common approach to pre-train BERT is to have it perform the masked language model task. In this task, 15% of the tokens in the corpus are randomly masked. BERT is then tasked with predicting each of the masked tokens. The loss is calculated based on the difference between the predicted probability distribution and the actual ground truth. And this loss is used to update BERT's parameters. This process allows BERT to learn contextual language understanding without needing labeled data for specific tasks. So because BERT uses masked language model task as its pre-training task, it can use whatever large text as its training data. So for Indonesian language, we also have a bunch of text. We can use it to pre-train the Indonesian version BERT. So for other language, we can use BERT. We can pre-train BERT on their own language. That's why BERT is so welcome and so populated. Another task employed to pre-training the original BERT model is known as next sentence prediction. In this task, the goal is to predict whether input 2 is here follows input 1 in the corpus. So to make this prediction, the output corresponding to the special token is COS is utilized. So positive examples for this task are generated by selecting any two consecutive sentences in the corpus. We can pick like 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. They are all positive examples where the model needs to correctly predict the input 2 indeed comes after input 1. On the other hand, negative examples are created by choosing any two sentences not belonging to the set of positive examples. They can be like 1, 3, 3, 1, 3, like 2, 1 is also negative examples. In this case, the model must predict that input 2 does not follow input 1 in these cases. This task helps BERT learn contextual relationship between sentences in the text. So we can see that the label here is next or not next. So indeed, the pre-training and the fine-tuning framework has become a prominent trend in natural language processing. In this framework, the initial step involves pre-training BERT using extensive data sets like the book corpus and Wikipedia, combined with the two tasks we discussed earlier. This pre-training equips BERT with a comprehensive understanding of language. Then this pre-trained BERT model is employed as the encoder. The encoder's output is direct to a downstream classifier, which is used for various tasks such as span detection, as depicted in the illustration. Compared to traditional machine learning frameworks, this approach offers advantages like the reduction of required training data because the pre-trained model already possesses a deep understanding of language patterns. It has significantly contributed to the advancement of NLP tasks and improved performance across various applications. So let's take a recap. We firstly undergo the semi-supervised learning step. We use a bunch of text corpus and use the two pre-training tasks to pre-train the BERT model. Then the BERT model has already understood the language. Then we use it to encode the input and generate a representation and send it to the downstream task output for classification or other natural language processing task. So BERT has two widely used versions. In BERT base, the embedding vectors have 768 dimensions. There are 12 layers and 12 heads. In contrast, BERT large uses 1024 dimensional embedding vectors and has 24 layers and 16 heads. In many practical scenarios, BERT base is the preferred because BERT large demands significantly more GPU memory and computational resources, making it less accessible and suitable for most applications. So in this illustration of BERT base, we get a clear view of the stacked encoders. Each token is initially processed by the first encoder, and the output from the first encoder is subsequently passed to the second encoder, continuing in this manner for each subsequent encoder layer. Importantly, these computations can be performed in parallel, which enhances the efficiency of BERT's processing of input tokens. Each token's embedding in BERT base is determined by the output from the 12th encoder layer. This approach ensures that each token has a distinct embedding that varies in different contexts. The embedding for a token depends on the entire context within the same sentence, allowing BERT to capture nuances and the contextual dependent context-dependent representations of words. Okay, certainly BERT as a pre-trained encoder can be fine-tuned for a wide range of specific NLP tasks. Fine-tuning involves taking the pre-trained BERT model and adapting it to perform tasks such as sentiment analysis, name entity recognition, question answering, and more. This fine-tuning process allows BERT to leverage its pre-trained language understanding capabilities to excel in various downstream NLP tasks. Indeed, BERT's function extends to a very variety of tasks when configured to accept two sentences as input and utilize the output token corresponding to the special token's COS token. Here are 4 tasks that can be performed using this configuration. The first is MNLI. This task involves determining the relationship between two sentences, specifically whether they are in an entailment, contradiction, or a neutral relationship. The second is QQP, Quora question pairs. The goal here is to assess whether the first question and the second question have the same meaning or not. The third is called QNLI, where it is question answering NLI. In this task, the aim is to determine whether the second sentence can serve as a valid answer to the first sentence, essentially checking if the second sentence answers the questions posted in the first. The fourth is called SQUAG, which is the abbreviation of situation with adversarial generations. The task is to decide if the second sentence logically follows or is a plausible continuation of the first sentence within a given situation or context. The configuration showcases BERT's adaptability to a range of NLU and inference tasks. So this image provides a clear illustration of the first configuration. It involves the BERT encoder followed by a classifier layer that takes the output corresponding to the CLS token as its input. This step allows BERT to be fine-tuned for various classification tasks by using the CLS token to make predictions about the relationship between two input sentences. So here we can see that this is the first sentence, this is the second sentence. Absolutely, when the input consists of only one sentence, the BERT model effectively functions as a text classifier. Here's a couple of examples of tasks that employ this configuration. The first is called Stanford Sentiment Tree Bank 2. This task involves classifying movie comments into one of three sentiment categories: positive, neutral, or negative. BERT takes a single sentence as its input and makes predictions about its sentiment. The second is called Corpus of Linguistic Acceptability, COLA. The task is to determine if a given sentence is linguistically correct or not. BERT, when configured for this task, takes a single sentence as input and assesses its grammatical correctness. These examples showcase how BERT can be fine-tuned to perform various of single-sentence classification tasks. The image provides a clear illustration of the second configuration, where BERT serves as the text encoder for single-sentence classification tasks. In this setup, the BERT encoder is followed by a classification layer that takes the output corresponding to the special token COS as its input. This allows BERT to make prediction based on the content of a single sentence as depicted in this diagram. So the third configuration is particularly suitable for machine reading comprehension tasks. In this setup, the question and the paragraph, which may contain the answer, are concatenated into a single string and fed into BERT. BERT then generates output that incorporates information about the answer's start point and the ending point and the span of the text that constitutes the answer. The configuration enables BERT to effectively extract answers from text based on the provided question and the context, making it a valuable tool for reading comprehension tasks. The fourth configuration is employed for sequence labeling task. In this setup, the input consists of a single sentence, and BERT produces tags corresponding to each token in the sentence. A classic example of sequence labeling task is name entity recognition, where the tags representing name entity types along with their position in the text. For example, in the provided example, the first token tag is O, which signifies other, while the second token tag is BPR, indicating the beginning of a person's name. The configuration allows BERT to identify and label specific entities or elements within the input sentence, making it valuable for various sequence labeling tasks. So we can apply it to like part-speech tagging and any task requiring sequence labeling. Both encoder and the decoder parts of the transformer model can be used independently for different NLP tasks. The encoder is great for understanding and processing input sequences, like in text classification or labeling tasks, while the decoder is useful for tasks that involve generating output sequences, such as translating text, creating content, or summarizing information. This flexibility allows you to choose the right part of the transformer model for your specific language-related task. So now we are introduce the second. One well-known transformer decoder is the generative pre-trained transformer, abbreviated as GPT. So we know that, as we know, the famous ChatGPT comes from GPT. In comparison to the standard transformer decoder, which we see here, the key difference lies in GPT's utilization of only the masked multi-headed self-attaching mechanism. This distinction arises because GPT lacks the encoder component found in the Manila transformer, making it especially suitable for tasks involving text generation or completion. GPT-2 is constructed by stacking multiple transformer decoders on top of each other, creating a deep architecture that excels at tasks like text generation and language modeling. GPT-2 comes in 4 different settings, ranging from the smallest to the largest: small, medium, large, and extra large. The primary distinctions among these settings are the number of layers and the model's dimensionality. So GPT-2 Small employs 768 dimension embeddings and comprises 12 decoder layers. In contrast, GPT-2 Extra Large utilizes 1,600 dimensional embeddings and boasts a total of 48 decoder layers. The choice of GPT-2 setting depends on the specific requirements of a task, with large models often offering improved performance at the cost of increased computational resources. Certainly, let's break down how GPT-2 works with an example. We begin by prompting the GPT-2 model with a list of tokens. In this case, we cite the first law. Then GPT-2 starting generating text in an auto-regressive manner. This means that once it generates a token, that token is considered part of the ongoing prompt and is used to generate the next token. So in this example, GPT-2 generates the first token A, which becomes part of the prompt, making the updated prompt recite the first law A. With this updated prompt, GPT-2 generates the next token, robot, which is added to the prompt, resulting in recite the first law, robot. This process continues iteratively, with each token generated by GPT-2 being used to extend the prompt and guide the generation of the next token. It allows GPT-2 to produce coherent and contextually relevant text based on the given prompt. Certainly, in the transformer decoder's multi-headed attention mechanism, the version used is typical the masked variant. The masked MHA ensures that the attention is not allowed to be directed toward positions in the input sequence and comes after the current position being considered. So this picture illustrates the difference between self-attention and the masked self-attention. So let's explore how GPT-2 generates each output token. To initiate the generation process, we input the start token, often denoted as S. GPT-2 begins generating the next token in the sequence. In this example, it generates the token the. The first token, the, that GPT-2 generates quickly becomes the second token in the input. Then GPT-2 proceeds to generate the next token, which is seen. To obtain the embedding for each token in GPT, it follows these steps. First, GPT starts by fetching the token's embedding from its dictionary of token embeddings. Next, it adds the positional embeddings for that token to the token embedding. This combination results in the final positional token embedding, as we just learned. So we have token embedding of S, we have positional encoding for token 1, and then we get the positional token embedding. This final positional token embedding is then used as the input for the first layer decoder. The positional token embedding of S is initially input into the first layer decoder. This decoder contains a MSA, multi-headed self-attention module, and a feed-forward neural network here. From there, the decoder generates an output embedding, which is then passed into the second layer decoder. This process repeats iteratively until the 12th layer decoder generates the final output embedding. In essence, each decoder layer contributes to build the output embedding through the sequential process. So generating the output token involves the generation of the first layer to the 12th layer. Imagine GPT has already generated 9 tokens from sentence begin to it. Here's what happens next. First, GPT calculates a score for each token by computing the dot product of its own query and the key associated with each token. Then, to make these scores more manageable, GPT normalizes them using a process called softmax. This ensures that the sum of all scores equals to 1, making it easier to interpret and use in subsequent steps. So we are now going to predict the word after it. Recall the self-attention involves a simple concept. For each token, we calculate its score by multiplying its query with its corresponding key. After applying, so we can see that we can multiply it with A's key, then we can get its weight or score. We can use it query. We can calculate the dot product of query 9 and key 2, and we can dot product query 9 with key 3 and any key. Then we can get the score of each word, each token. After applying softmax to the scores for all tokens in the sequence, the sum of all scores equals 1. For example, we can see that GPT allocates 50% of its attention to robot and 30% to A. The token immediately following it is primarily influenced by robot in this case. So we dot product the value vector and the corresponding score vector. Then we can get the influence portion of that token. Then we sum up all these value dot product score. We can get the sum of the final result. So to calculate the probability distribution over the vocabulary, we simply multiply the output from the 12th decoder with the token embedding matrix. So these are the probabilities assigned to each output token, often referred to as logits. For example, the log probability for Aaron is 0.46. We randomly select a word from this distribution. In this instance, the is the word that was selected. So although this is a distribution, but we not necessarily select the word with the highest probability. We may select other word with second best probability or third best probability based on some randomness. So now let's delve into the specifics of GPT-2's masked self-attention mechanism during the evaluation time. Suppose the first token is A. For efficiency, GPT-2 keeps keys values and keys. And for efficiency, GPT-2 keeps GPT-2 keeps A's keys and the values in every decoder for later calculation, because in calculating the following tokens, these values will be used later. When robot is input, calculating robot scores requires A's keys and the values in every layer. Since these keys and values are stored when A is input, there is no need to calculate them again. So key 1 value 1 was generated when input was A. Key 2 and value 2 was generated when input is robot, and so on. When it is the input token, its positional embedding is used to create query, key, and the value vectors. GPT-2 uses 3 metrics to generate query, key, value vectors. So based on this, we can generate query, key, and value. The 768 dimensions can be split into 12 different attention heads. Each has 64 dimensions. Every head has its own query, key, and value, and works separately. For example, head number 1's query, key, and value are denoted as Q91, K91, and V91, respectively. So now we focus on attention head number 1. By multiplying Q91 and each token's key, we can obtain each token's value. So by applying softmax to these values, we can get each token's ratio of influence on the 10th token, which we are going to predict. So we can see that the influence score for the 10th token, the 3rd token, robot, is highest, and then A, and then it. By multiplying each token's ratio and its value, we can get 091. Then we concatenate all heads Z vectors, resulting in the final Z vector, Z 9, 1 to 12. So this is the result by concatenating the results of all heads. Then linearly transform the result of multi-headed attention into an output vector. here and pass it to the point-wise feed-forward network. Firstly, we linearly transform Z9 from 768 dimensions into 768 multiplied 4 dimensions. We expand the dimensions. Then we linearly transform these enlarged dimensions into its original dimension, 768. This picture summarizes how R9, the output at the ninth position, generates by the decoder. So firstly, we split into 12 heads, and we use 12 different transformations to create 12 sets of QKVs, and then we obtain the result and concatenated the results to be one output again, and then we use 2 transformations. One is expanded from 768 to 4 times big, and then we shrink the 4 times big vector back to the original size. Then we get the final decoder's result. Now we are going to count the number of parameters in GPT-2 small. So layer by layer, each layer has its own set of weight matrices. The entire model has only one global token embedding matrix and the positional encoding matrix. In a single transformer layer, there are 7 weight matrices used for different transformations. First is the weight matrix for converting the input into query key and the value, has 768 multiplied 768 multiplied 3. And the matrix of transforming multi-head attention output into the final Z vector has dimensions of 768 multiplied 768. Third, the matrix for transforming the final Z vector into a vector that's 4 times wider has dimensions of 768 multiplied 768 multiplied 4. Fourth, the matrix of reversing the transformation from 4 times wide to its original dimension has these big parameters. 5, the weight matrix for layer normalization and has dimensions of 768. Approximately, when we sum up these parameters for each block, we end up with approximately 7 million parameters for each block. So since there are 12 blocks in total, the results in total of around 85 million parameters. When we add the parameters from token embeddings and the positional encoding, the overall count comes to around 124 million parameters for entire GPT-2 model, small. So now let's explore diverse range of applications where GPT can be used beyond its primary function of language modeling. You can transform GPT-2 into a machine translator by giving some English-French sentence pairs as prompt. Here we have several, and we prompt it, and then we feed a new sentence without output, then it will generate the French part.
Comment allez-vous?
Next, here has a standard Wikipedia page structure. As per its format, the pink block serves as the summary section, and the green part is the article itself. By providing several article summary as prompt, you can turn GPT-2 as a article summarizer. This is called few shot prompting. Okay, so that's end my talk today. So is any question?
Okay, thank you, Professor Richard, for the presentation. So now we will Q&A. So for student, if you have any question about the transformer model, this is the basic of current LLM, popular LLM model. So is there any question from students? Okay, Professor Richard, we have a question from chat.
Yeah.
What is query K and value factor? How do we define the word embedding into them?
We use actually they are generated from our original word embedding. We use 3 different linear transformations to generate them. We use 1 linear transformation to generate key, 1 to generate query, and 1 to generate value. So if we have 12 heads, we have 12 sets of transformations. And the parameters of these transformations need to be trained using our training data.
Okay, thank you, Prof. Richard. So is there any other question? Professor Richard, maybe I want to ask you some question.
Okay.
You know that today we maybe every day there is a new large language model that appear in Hugging Face, for example. Do you have any conclusion? What is currently they propose? I mean the difference between one model with the other. Is there just any different size of data set, or how can you comment it?
So let me rephrase your question. You mean that there are many publicly available large language model that can be downloaded from Hugging Face? What are their differences?
Yeah, I mean, are they the new one is just different data set, or maybe has different size of model, or anything else?
Okay, that's a very good question. I think they basically based on the GPT-2 architecture, so you can think them almost the same, but they only have a little bit difference in deal in the self-attention part. Some model they modify the original self-attention part so they can deal with longer context, but um, some did not, because if you change any part, then it will influence the performance a lot. Maybe you improve you extend the ability to longer context, but you sacrifice the performance on shorter context. So that's a trade-off. You must consider that.
Okay, I got your point, Professor Richard. And how is the you know that the model size is very large currently, and standard GPU card or GPU processing unit maybe cannot be used for processing that large size of model. Did you ever has experience to using the large size model in the public one? Is there any techniques to make our, for example, standard graphic card by using that large model?
So let me clarify your question. You mean that when we want to use a very large size model, we may encounter the problem of resource intensive. So how do we deal with that problem?
Yes,
Is that right?
correct.
Well, currently, there are two solutions. One is to use PEFT, PEFT, which is that we use adapter. We attach adapters to the original model. Then we use our own data to tune the adapters, because the parameters of the adapter is much smaller than the number of the original model. So it can let us to fine tune the large model. The other way to fine tune the large model is to try to use low precision um, um, data, low precision, try to lower the precision, like from 14.16 to quantum size it. So there are many implementations of that kinds of solutions. That makes you can train your own Llama-based Llama 7B on your own computer. So you can search a you can search a GitHub code llama.cpp. Then you can find related information.
Okay, yeah. We face that problem. So many students here also implementing the large language the LLM, but they face the problem that the resource is not enough to load the large size the model. Okay, and you also mentioned in your presentation Indonesia is one of the low resource language. We have resource, but maybe the resource is not collected yet. So bahasa Indonesia or Indonesian language is one of the low resource language. But currently we already have the Indo bird version that trend from bahasa Indonesia. I
Mhm.
think uh in your opinion, what should we do as a researcher
Mhm.
to generate more good or better model? Should we just use the existing dataset, or we try to collect it more? Because you know that the large scale datasets is come from industry, not from university or academics. Uh, so which one first, uh, if you have any opinion, collecting more large dataset, or building model from the existing dataset?
Okay, that I can understand your question. Your question is, do we need to collect more data um regarding the from academic or industry, or we just focus on existing academic data set?
Yes.
In my experience, I think data more is better for pre-training. If you can collect more data uh, for a low resource language, it is better. Yeah, I think Indonesian is still in the stage, but for a plentiful resource, plentiful language like English, then they can select the most meaningful part. Like I have read several papers to suggest how to select good quality pre-trained corpus. Yeah, so I think in this stage, I think Indonesian researchers still need to collect more and more data, and more is better because more the data collected from industry covers a different aspect from than its counterpart in academic world.
Okay. Uh, I think enough from me. Is there any other question from student? So this topic actually is like uh more advanced that from the previous lecture, or our discussion in class, but we need to know that currently uh there are so many variation of bird, or maybe transformer. So transformer is it can be say that this is a basic of uh, the GPT, or maybe bird itself.
Mhm.
Okay. So one more question, I think. Uh, in the chat, Muhammad Gustaf asked that about multi-headed attention. Uh, the feature token are discarded, but what is feature token means?
Feature token means the token update.
So the token update. Yeah.
So because in the encoder part, you can see the whole sentence, but in the decoder part, you only like we have already generated three tokens, then you only know these three tokens. You don't know the fourth token, so you cannot attend to the fourth position.
Is this enough, Gustav? Okay, so if we enough, or there is no question, I think this is the end of the uh, class from Professor Richard. Thank you very much, Professor Richard. This is your second lecture. Maybe we will meet once more, but you are not taking the class, but we will discuss about our curriculum in text mining. So we will contact you later by Mr. Fadli. Thank you very much for all of the participants and see you. Good afternoon.
Thank you, Thank you, Professor Rizzo. Thank you.
Yeah.
Thank you, everyone. Thank you.
Thank you, Professor.